know that any of these words are really worthy of recording for posterity, but so be it. I'm going to talk a little bit about some work that was finished about half a year ago with Stefano De Angelis, who was formerly a postdoc at Saclay and now has a CNRS, permanent CNRS position, and Giacomo Brunello, who was at the time a PhD student and is now a postdoc at in Pisa. And of course, the two younger people did most of the heavy lifting, all of the really difficult technical parts. Now, I realize this audience is a somewhat unusual mixture of people who are more expert than I am, people who are probably on this particular subject much less expert. And so in the usual style, I've tried to design a talk to bore the experts for the first half and to lose the non-experts in the second. So we'll see how that goes. So our subject is gravitational waves. And I'm sure you've seen this picture and many other pictures like it over the years. This one is courtesy of LIGO. And we have, well, depends how much insider knowledge you have, but let's say of order 200 confirmed events in a decade since the first very loud event was seen. And the last run, O4C, ended in November. And I'm not exactly sure whether they're going to start running again soon or whether they're going to take time and a shutdown. Most of the events are mergers of binary black holes, some neutron star mergers, some mixed. Again, you've probably all seen this what I like to call the batwing plot. It's interesting because, to be fair, people didn't really expect certainly this many binary black hole events. Ricardo Stirani, who's involved also in LIGO, claims to me that actually there were predictions. But if you look at the predictions, before LIGO started, the uncertainty bands stretched over 4 orders of magnitude, which to me kind of means you didn't really know much. Now, in addition to a very interesting present, there are future plans for gravitational wave observatories of the same interferometric style. And the main lesson you should be pulling from this plot is that we are expecting an order and a half of magnitude improvement in sensitivity with a concurrent somewhat widening of the frequency band. These are all observatories that are the multi-hundred hertz frequency band. And I can't actually update you much about the Cosmic Explorer. He presumably knows more about its current planning than I do. But this year, next year are kind of the make or break years for the Einstein telescope, which there are two competing proposals, one of which is a underground triangular single site proposal on the Dutch-German border. And the other one is an underground, more traditional L shape with one site in Sardinia, and probably the other site to be proposed is on the Polish-German border. Now, much of what I know about this comes from a source in Geneva who's actually promoting the Sardinian proposal. And so I'm not sure that it's completely unbiased, but we can enjoy it for those who know. One of the interesting things I did learn from talking to him that you might wonder about geological stability, that it turns out that geologically, Sardinia is actually part of Africa rather than part of Europe. So that's good. Anyway, the main issue will be once the site is chosen, how much enthusiasm there will be for the non-local government to continue funding it, because it's not really clear what European mechanism it will be, but I'm still hopeful that the project will go ahead. And first observations should probably be in somewhere between 2032 and 2034, assuming everything goes forward. So what about the science goals of these big instruments? And again, the scale, the financial scale here is less than, let's say, a new collider, but it's still substantial. It's on the order of 2 billion euros for the Einstein telescope. So when you either extend the sensitivity or open a new window, you have the right to have unexpected discoveries. And I would say that the black hole binaries was something that they had, that LIGO had the right to discover something unexpected. And I think we have every right, or let's say the Einstein telescope collaboration has every right to expect some surprises when they turn on. Of course, there's the long-standing question of neutron star equations of state, and in some sense, the connection to the Earth beneath our feet. How much do neutron star mergers contribute versus supernova to transferic element production? There are more exotic questions, such as, do some neutron stars have an inner core which is quark matter, which is still an open question, and which potentially could see answers in the coming decade and a half. There are ideas which people are already pursuing to measure the Hubble constant. Not my area of expertise, but everyone knows that there's a tension between kind of the very deep measurements, the high Z measurements and low Z measurements. And here there are really two approaches. One is to try and use individual events where you have an electromagnetic counterpart, which there are a handful and there will be more, to use them as bright candles, and also to use dark candles statistically to make a measurement of the Hubble constant. We can expect limits on exotic compact objects, and also strong field tests of Einstein gravity. And if some of the more speculative ideas of some of my colleagues and others are correct, perhaps even some insight into quantum gravity. Well, this is all very nice, and maybe this audience has seen this before, or at least many people have, so I don't need to spend too much time on it. But what are theorists doing? Well, it's the key thing one has to understand about all these detections, that except for the very, very loudest of signals, the noise level is typically much, much larger than the signal, even after filtering. So this is for the very famous initial event. This is kind of what the raw signal looks like. Then you filter it, and on the inside here, you're trying to pull out a signal that looks something like that. And I draw your attention to the scales involved here. So that this is 10 to the minus 18 in strain. This is 10 to the minus 21. So in fact, this signal on the scale of the raw data is basically a flat line. So in order to pull the signal out, you have to know, in some sense, something about the auto temporal correlations inside the signal. And for that, you need what are called templates, theoretical templates. And that's where theorists come into the picture. And of course, once you detect an event, you want to measure its parameters, the spin, the masses. And for that, again, you need a more detailed set of templates. Now, to some extent, you could argue that for actual detection, we already have enough templates, at least for LVK. But going forward, the better and more precise templates you have, then the fainter signals you can expect to see. So improving your templates also can contribute to improving the reach of of these telescopes. So the basic setup in mergers, we have two slowly inspiring compact objects, for example, black holes. And working backwards in time, then there's a ring down after the two black holes, for example, merge into a final black hole. The thing rings like a bell for a while and then eventually returns to become quiescent. And there you can predict the gravitational waves from an understanding of the normal modes of the resulting black hole. That's not something I'm going to talk about anymore. The very merger itself, of course, is strong field, is a strong field calculation, and that's where you want to use numerical activity. And where the theorists, where the explosion in activity in the last decade has come, is in the inspiral field, where we can do weak field perturbation. One of the challenges is to try and push this weak field perturbation theory as close as possible to the last few orbits where one then matches on to numerical relativity. Some people sometimes ask me, why is it you don't just do everything with numerical relativity? And the answer is that it's basically money or computing power, however you want to phrase it, that you ideally want libraries of a couple 100,000 templates, and it would take longer than the lifetime of the universe to generate that many with numerical relativity. A single template is a couple of months work on a cluster. There's also issues that it's very, very hard to do long inspirals. That will be more an issue in the LISA era, when there'll be very, very long weak field inspirals that you'll see. So this is a problem, of course, which traditionally is tackled in the classical general relativity. And you might wonder, why are people like Zvi here, or like me, who have a background in quantum scattering amplitudes, pursuing this problem? So of course, there's 3 decades of innovation in technology of doing these calculations and understanding of how to apply basic physical principles, factorization, unitarity, calculate only what's really needed for physical quantities and ignore the stuff that isn't, and banish the unphysical parts of Feynman diagram calculations. But at least what was part of the sales pitch, and maybe has not been quite as much of played an active role, is that of the double copy, the basic idea that you can take a calculation in gauge theory and double copy it to a calculation in gravity. And the resulting pathway is much, much simpler than following Feynman diagrams for quantum gravity, which are essentially the same diagrams as for classical. So the state of the art, which I hope I'm to give a similar talk in a year's time, I will be able to say somewhat different things, is that we're focused on calculating things in the scattering domain, not yet directly in the bound domain. And there are several different approaches. I'm going to focus on the one that my collaborators and I have pursued over the years, where the connection, let's say, to the actual observations is a little bit more complicated. So we imagine we're scattering 2 charged things. They could be charged under QED, or they could be massive and therefore charged under gravity. And we're going to treat the black holes here as point particles. So in the spirit of an effective field theory, where the size of the object is much smaller than their separation, and which in turn is actually going, because of the weak field approximation, is going to be much smaller than the wavelength related to radiation. So here we're going to look at the radiation that's emitted during the scattering of these bodies. And going to follow the approach which the community has decided should be called KMOC, although the part that's going to be relevant today was also done with two younger guys, Andrea Cristofoli and Ricardo Gonzo, who, as is my usual habit, are both in bold because they're still looking for jobs. So keep them in mind if you ever have the occasion. So we're going to study physical observables. We're going to start from a quantum observable and take it to the classical limit. Well, the first thing we do is we restore H bar by dimensional analysis because we want to take H bar to 0. And the key thing, other than putting the H bars back in the couplings, turns out to be that we need to distinguish wave number from momentum for massless particles. So here, of course, we're not scattering plane wave states. We're interested in scattering lumps of stuff. So we build an initial state using relativistic wave functions. The precise form of these wave functions, at least at low orders in perturbation theory, is not that important. There is a phase space for the massive particles. There are these relativistic wave functions. There's a phase which is encoding the impact parameter, the separation. And then these are just built out of products of plane wave states. So it's the localization is coming through the relativistic wave function. So we now think of the S matrix as the evolution operator from the far past to the far future. So we write the outgoing state as the action of the S matrix on the incoming state. And generically, the observables that we're going to be interested in are looking at some change in some object. So some final state expectation value minus the initial state expectation value. And wherever I've dropped the subscript on the state, it's the in state. We can now expand the S matrix, and then using unitarity, we can obtain an all orders master formula. So the change in some observable, there's what I call the virtual loop contribution, which involves a single transfer matrix. And then there's the so-called cut contribution, which involves two of them. Cut because you would do this by inserting a complete set of states. And these two are all order formulas. Each one of these things has an expansion order by order in perturbation. So that is, in fact, a prediction which is valid in the quantum theory. And we now want to take the classical limit. So there are three scales that we have. We have the Compton wavelength of the massive particle. We have the spread of this relativistic wave function we've put in. And we have the impact separation of the two trajectories initially. And it turns out that not too surprisingly, the scattering length is sort of going to be comparable to the impact parameters. So you can think of this as a hierarchy of those scales. You want the particles to be localized, and you also want the wave packets to be well separated so that the particles are not peering inside each other. And you can do this analysis more carefully, and you find what I've called the Goldilocks condition. You need this hierarchy of scales. And when you're turning the crank here, then we're going to see this a little bit more in detail in a few minutes, that you're going to express these observables in terms of amplitudes. And then as you're taking the classical limit, you can have singular terms, things that go like 1 over h bar, 1 over h bar squared in the intermediate stages, but they will all cancel in the final result, fortunately. So that's the setup, which includes both global observables, things like the impulse, the net momentum change, the total emitted radiation, things like that. But we can also study a local observable. So imagine we have our scattering region, so our two particles are scattering, and we can think of it as mostly happening in some localized region, because even though it's a long-range force and there's always radiation, at some point or other it falls below a noise floor. And then it propagates many directions, but we only have an observer in one direction. So I've chosen here to represent these very sophisticated telescopes by a pair of Mark I eyeballs. And so we have some current, and then we can build an observable in that direction from the propagation. And the waveform is the leading large distance behavior. Given the incredibly large distances involved, the next term in that expansion is completely invisible. So we can turn a very similar crank for the waveform at the expectation value of nu in vector dynamics, or here the Riemann tensor. And this would be if there's any radiation in the initial state, generally speaking, we assume not. And so then we have, again, two terms which we can write in the same form that I showed above, the loop and the cut, but it's actually a little bit more useful here to rewrite them in a slightly different form. And the key thing is that the first term is the only one that shows up at leading order. The cut term is something that shows up only at next to leading order and beyond. And of course, this term has an expansion to all orders in G or kappa, as does the second term. But it's only at next to leading order that you have to include both. So there have been lots of waveform calculations in recent years. In fact, in a certain sense, the leading order calculation was done by classical general relativity approaches almost half a century ago. And it's one of the plots that I sometimes show during the colloquium about the progress in W plus NJet calculations, kind of like a decade for each one. Well, here, going from leading order to next to leading order was closer to half a century. And I think I'm not going out too far on a limb to say that it's not going to be another half century before we get to the next to leading order of calculation. So there have been a number of NLO calculations, including by people in the audience, Radu and Matteo. And so, well, with this very impressive list, which have had certain cross-checks in between them, what's the point of doing another one? So that's what I'm going to try and talk about in the second half of the talk. So a lot of the change here is more interest to the experts. We're focusing directly on the frequency domain waveform, and kind of the key technical idea, which we haven't done fully here, but it's, think of it as gearing up to do it more fully in NLO, is to combine the Fourier and loop integrals and really treat them on the same footing as far as IBP reduction is concerned. So that was done. The thing that hasn't been done is that you can also imagine calculating them via differential equations again on the same footing, and that's something which is technology for the future. And well, I guess that's maybe in the eye of the beholder, but I think the expressions that are in our paper are somewhat simpler and more tractable. So instead of working with the Riemann tensor, we work with a linearized gravitational field operator. And the Goldilocks condition become this set of extreme inequalities. So the impact parameter compared to the distance to the scattering black holes, and then the radius of each one and the Compton wavelength. So we can write the frequency domain waveform here. And this is just a transcription of the more generic formula that I showed you a few transparencies back. So of course, the T matrix in between two states up to a delta function, that is just a matrix element. And the one that has two T matrices, as I mentioned there, you insert a complete set of states, and then each of the matrix elements, again, is just going to be a scattering amplitude. And there's a sum over the intermediate states. Of course, at any given order in perturbation theory, there's a limited number of states you can insert. So the measure here has what looks from the point of view of the amplitude like a momentum transfer, but in a sense is a mismatch between the incoming and outgoing state wave functions. And they're corresponding what's left over from the on-shell phase space measures of the massive particles will give us some delta functions that are going to pinch some of the lines. And of course, the rest of this is fairly standard and usual momentum considering delta function and the phase factor, which is implementing the impact parameter. So I mentioned that we combine the master integrals. So we treat the loop and Fourier integrals together. And again, so we're going to write the waveform as a sum over these basis integrals with coefficients. The coefficients, as usual, are rational functions of the various invariants and in principle of epsilon, although the dimensional regulator dependence here is simple. It turns out to be helpful to use a slightly shifted set of momenta absorbing some of the momentum transfer in order to simplify the structure of the delta functions. And finally, we now have integrals which are functions of five invariants. The emitted graviton momentum dotted into the four velocities of the two scattering particles, the impact parameter squared, the relative angle of the impact parameter, and the graviton momentum, and the Lorentz factor of the two scattering particles. So we construct the integrand from cuts. The only shortcut here is really that terms that are going to be ultimately local in the Fourier transform get dropped very early on. And again, the cuts that are relevant in the classical limit and other simplification are those that correspond to the massless lines in the diagrams. The internal graviton state sums one can do as in dimensional reduction, and as is completely standard in amplitudes, all the external momenta we take as four-dimensional. Okay, so we have a loop integral, and we also have a Fourier transform. The Fourier transform, of course, is present in the lowest order calculation as well. So in a sense, you're starting from always having at least one integration to do. And we have the indices corresponding to the various denominators that can arise here. And in the usual way, I'm writing the numerator as a function of the two integration momenta of the loop for the transform. So we have some of the numerators that, some of the irreducible or reducible invariants that only show up in the numerator, including one that shows up as exponential factor. That's the one the impact parameter. And we have another one that also shows up only in the denominator. So it's written in the numerator. So it's written here in the usual IVP notation, where it's written in the denominator, but secretly the corresponding index, the corresponding exponent, is negative. There are some that show up only inside delta functions when you treat those by reverse unitarity. There are some that will be pinched into delta functions by taking the classical limit, again, same treatment. And other ones show up as genuine denominators. So we end up with two families of integrals, where some of the indices are going to be fixed, and other of the indices, and in fact, the other family is just you get by switching A6 and A7s. And here you can think of these as being kind of cousins of two-loop integrals. And so there's going to be a machinery, both at the IVP level and presumably looking forward could be at the differential equation level, and also in terms of symbology and the whole infrastructure that has been built up for loop integrals over the years, there should be a cousin of that that can be applied here. And we're just taking the first step here. And how many people actually know what a twisted period integral is? Wow. Arachnis. Yes. So these things are indeed examples of twisted period integrals. The twist here, I guess, in some sense, is coming not only from the dimensional regulator, but also from the presence of the exponential. But the main message of that line is that sometimes advisors can learn something from their students too. And this is something I learned a little bit about from Giacomo, who's actually an expert on the subject. So we do integration by parts in a more or less standard way, except that we consider differentiating not only with respect to the loop momentum, but also with respect to the Fourier transform momentum. And essentially the IVPs that you get are kind of weighted sums of ordinary IVPs. And then a certain amount of teeth gnashing, Giacomo was able to feed it through light red with using finite field technology as implemented in finite flow.
How related this is to people? Maybe even you discussed this generating functions or like these IVPs.
Yes. So
intervals with great dots.
So that would be a tangent. It's also something I've been thinking about recently for precisely these kinds of applications. We did not use any of that technology here. It was kind of more standard off-the-shelf IVP codes. But yes, that is technology that I believe can be used to simplify these reductions. And I would say that kind of a real world test of that is probably somewhere between 6 months and a year off. So, I mean, there are syzygy-based programs like Neat IVP written by Yang Zhang and things like that, which some people are using, but at least a more modern approach using that is still under development. And if you want to know more, then I'm here this week. Come talk to me. So it turns out that each of these two families can be written in terms of 76 master integrals, but only 28 of those integrals actually appear here. And I believe that Giacomo was able to show that, at least for the first and second order in spin, it's the same integrals that show up. But I'm not 100% sure that's it. So there's certain sets of denominators that show up. And one of the kind of paybacks from doing things in a combined way is that the set of integrals that we would have to deal with, if we did first the loop integral and then we did the Fourier transform, we have to deal with a larger set of integrals. So even though we haven't done the differential equations directly, we're already dealing with a smaller set of integrals. So the other thing that we do is we choose the basis of these combined master integrals, CMIs for short, so that the coefficients are finite as epsilon goes to 0. So we remove any singularities in coefficients, and that can be done algorithmically. This is work with Stefano and Yang Zhang, some of Yang Zhang's people. And without, again, hijacking the time here to go through this in detail, the basic idea is you look at the epsilon free part and you reduce that. That gives you an over-complete set of master integrals, and there are now going to be singular coefficients which you clear, and then you iterate this until it converges. So of the 28 integrals that appears, you can further subdivide them for purposes of actually calculating them into a set of integrals which you need to calculate directly, and then others which you can obtain by differentiating with respect to the impact point. So after we do all of this, we find a result for what we're saying is the waveform, which is infrared divergent. And that doesn't seem very happy. And it reflects the fact that we haven't really expressed the observable in the sense of what the experiments observe precisely. And it's not a problem which I know how to solve today, but I'm sure that there is a solution, which is probably not too complicated. And were we to be able to do that in the spirit of collider physics, then we would actually do a computation which is manifestly finite. Nonetheless, we're close in the sense that one can see that the divergence does exponentiate. It's not an incredibly constraining check at next to leading order, because you just need to see that the divergence is proportional to the tree, which is a non-trivial check on the calculation, but it is in fact satisfied. So you can exponentiate that divergence and the fact that it's actually an overall, you can write it as an overall phase times the tree. Of course, an overall phase is not something you're sensitive to. So it's clear you just need to have an observable, have an expression for an observable which makes that phase independence more that. So, as I said, one can imagine thinking about doing combined differential equations for these combined master integrals. So, and that is probably something that's going to be essential to go beyond next to leading order, but that wasn't done here. So first one evaluates the loop integral. So it has certain result both in terms of the external invariance that I mentioned earlier, the W's, and also in terms of the Fourier momentum, which we still have to integrate over. And here, in spite of having masses and stuff like that, the results are actually tamer than one would expect from a full field theory calculation, because we basically have logarithms, there's no log squares, and there's no polylogs. And I don't know the proof of this, but it's kind of generic in these classical image calculations for gravitational waves. So having done the loop integrals, we then need to do the Fourier transform. And a convenient way of doing that is parameterizing in terms of the basis of four momenta. There are three natural ones, which is namely the adjusted four velocities of the two particles and impact parameter. And then using the epsilon tensor, one can build another vector, which is orthogonal to these. And this vector also can be made to carry the epsilon dimensional components, but in fact, that those components are actually relevant only to the order epsilon terms. So one doesn't even have to worry about it. One now does this by the various z integrals, either using the delta functions for z1 and z2, or by doing contour integrals. And this is a combination of analytic and I guess some stuff that NLO did numerically. So you have a picture where you have a variety of branch points, and there's a very intricate subtleties about matching contributions. You do an integral around the branch point, and then you match it on to the integration out to infinity. And in some of the integrals, you'll actually have logarithmic divergences from the circle, and then logarithmic divergences from the straight line, and you have to ensure that they cancel. And again, that was stuff that Giacomo did. And to actually do this analytically, in some cases, you need to rationalize the roots. Okay, so the people who, like Zvi, who have focused on calculating the conservative dynamics essentially by 4 points and then matching to an effective Hamiltonian, which you can then translate directly to bound state predictions. They're able to go out to g to the fourth and maybe g to the fifth now. We're working. And some of their competitors, if I may say so, have already published some results on g to the fifth. But...
Oh, so we were first.
Okay, all right. So and here we're only doing next to leading order, so that may seem as very far away. But in fact, the power spectrum, we're almost at the same level. We would need to do NLO to get to g to the fifth. And the other point is maybe not yet so incisive. Once we understand the analytic continuation, though, then having the full behavior will give you much more information about away from circular orbits. And that's actually a point which is worth emphasizing, that there's potentially stuff in the existing LDK data which is waiting there to be fished out by having the right templates. They have some kind of generic searches for periodic signals and for other things, but if there are more complicated waveforms that are waiting there, maybe even scattering type, or certainly very large eccentricity capture type events, and unless they're very loud, they would not have fished them out yet. So there may be things that are waiting for a new generation of calculations to be able to pull out.
When you say of the power spectrum, you mean completely differential also in the angle on the sphere?
We could do that. What I'm actually going to show you is just the differential and frequency integrated on the sphere. But yeah, we could do that. So in fact, this is going to be the integrated over the celestial sphere, summed over both the polarizations, and we take the waveform and multiply by the frequency and square that thing. And one of the things that's useful, not something that I've done, although something Stefano has done, is that to compare the results here to the post-Newtonian calculations to relatively high order. So again, doing cross-check. The numerical results I'm going to show you were done using something called Lebedev rules, which are numerical integration rules on the unit sphere. And the basic idea is that as you go to higher and higher order rules, you integrate spherical harmonics up to that order exactly. So it's kind of like an analog of some of these Gauss-Laguerre type numerical integration rules, but here for the unit sphere. And of course, at leading order, then it's just the square. The next to leading order correction is an interference term of the lowest order waveform with the next to leading order correction. And you can do this without too much grief. I mean, there's always some grief involved. Because here we have analytic expressions in terms of the integrals and the coefficients. And so this is something where you can run relatively large scale calculations. So this is in the frequency for a variety of choices of the Lorentz factor. And here also for different symmetric mass ratios. And the main message here is, I mean, you can see, again, the numerics here would depend a lot on the specific system, the importance compared to the leading order, and so on and so forth. But there's a fairly large sensitivity, for example, to the Lorentz factors. And then the power spectrum. So this is the leading order power spectrum. And this is the next to leading one. Again, the relative normalization of this is very dependent on the specific parameters of any given event. But I think the thing that's interesting to see is that the shapes are actually quite different. And so the likelihood there is that once the sensitivity becomes, once the event becomes sensitive, then you're going to get some leverage on various parameters from going to higher order. And with that, let me come to my summary slide. So from a technical point of view, the kind of key idea of the more recent calculation is to treat the loop and Fourier integrals together. And that's something where you'd like to actually push forward and do the whole differential equations technology also combined rather than the separate options. And that we've put together into a relatively compact expression for the next to leading. So let me stop here. Any questions, comments?
So this fact that you can do the loop integrals and Fourier integrals together, does that give you some insight into why you've done with polynomial?
So again, I have to be careful here because the organization of the basis integrals was done together. The actual evaluation of them at the moment is still done separately. And so the absence of polylogs, that's actually more linked to the classical limit. And I don't know the proof of this, but it's a generic feature that in some sense the transcendentality in these classical limit calculations is generically half of what it would have been in the field theory. And there probably is a way to prove it kind of generically, but I don't know.
I thought it was very clear talk.
Thank you.
Thank David again.
Tea is